Our next lecture is on determinations of crystal structures by XRD patterns. So, before going to start, let us know that how it has come. So, since 1913, when W. L. Bragg solved the structure of sodium chloride, the structures of many thousands of crystals, organic and inorganic, have been determined. Crystal structure determinations is very important because as the properties of substance are never fully understood until its structure is known. It is a necessary prerequisite to any understanding of phenomena such as the plastic deformations, alloy formations or phase transformations. So, actually if we want to know the physical properties or maybe the chemical properties of any kind of materials, so we have to know the crystal structure of that particular materials. Since structure determines the diffraction patterns, the structure should be deduced from the pattern itself. So, what are the basic principles involved in structure determinations? So, if we talk about the unit cell crystal structure, it is called the line positions, and if we are talking about the atom positions, then it is called the line intensities. So, first we have to know what is the intensity of the diffracted beam. So, generally the intensity of a diffracted beam is changed by any change in the atomic positions. X-rays which are scattered first by a single electron, then by an atom and finally by all the atoms in the unit cell. So, from here you can see when we are talking about the scattering by a crystal, so first electron is coming. From that electron we can get the polarizations factor, then we will talk about the or maybe we will get the informations about the atom. So, from atom we will get the atomic scattering factor or maybe in small it is known as the F, and then after that we will get the informations about the unit cell or maybe the structure factor. So, first we will discuss about the first sub theme, that is the scattering by an electron. So, generally the X-ray are scattered in all directions by an electron. The radiations will be polarized along the directions of its motion. So, the intensity I p of the beam scattered by a single electron of charge E and the mass m at a distance r from the electron is generally I p is equal to I 0 by r square e to the power 4 by m square c to the power 4 whole multiplied by 1 plus cos square 2 theta by 2. So, in this particular case you can see that 1 by cos square 2 theta by 2, which is nothing but known as the polarization factor, which comes into being as we use the unpolarized beam, where I 0 is the intensity of the incident beam, c is the velocity of light and theta is the Bragg's angle. So, from this particular image you can see that electrons is there when the incident beam is coming to and fall upon the electrons starts vibrating, and then after that the diffraction pattern is going into different directions, and from these we are assuming that the diffraction pattern is following the x path and following the z path, and we are taking the resultant of that deflected beam. Now, we are going to discuss about the scattering by an atom. So, when an X-ray beam encounters an atom, each electron in it scatters part of the radiations coherently. So, scattering by an atom which is directly proportional to the atomic number, which is nothing but the path difference suffered by the scattering from each and electron and the lambda, which is nothing but the wavelength. So, scattering by an atom is equal to f into z, theta and lambda. So, here theta and lambda is nothing but the relation in between the theta and lambda is that sin theta by lambda. So, from the atomic scattering factor, f is known as amplitude of the wave scattered by an atom divided by amplitude of the wave scattered by one electron, which we can easily see through by this graph itself. So, here in this case the f is increasing, and in this case the sin theta lambda per angstrom it is increasing into the x directions, and from here you can see that the f, if it is higher and then if it is going down, so automatically the sin theta lambda per angstrom is also coming down. So, the scattering factor is sometimes called the form factors also, because it depends on the way in which the electrons are distributed around the nucleus. Next we are going to discuss about the scattering by a unit cell. So, the resultant amplitude of all the waves scattered by all the atoms in the unit cell gives the scattering factor for the unit cell. The unit cell scattering factor is also called the structure factor, which is nothing but known as a capital F. So, scattering by an unit cell is equal to function of positions of the atoms and atomic scattering factors. So, here F magnitude, which is nothing but known as the structure factor, is equal to amplitude of the wave scattered by all the atoms of a unit cell by amplitude of the wave scattered by one electron. So, here I directly proportional to F square. So, now we are going to discuss about the F n h k l is equal to summation over j is equal to 1 to n f z, which is nothing but the form vector or maybe form factor, and then exponential to the I phi z is equal to summation over z is equal to 1 to n f z e to the power I into 2 pi h x z prime plus k y z prime plus l z j prime. So, in this particular case f j is the form factor for the jth atom, h, k and l are the Miller indices of the h k l reflections, x j prime, y j prime and z j prime is the coordinates of the jth atom. So, the structure factor F is independent of the shape and size of the unit cell, but is dependent on the positions of the atoms within the cell itself. So, what are the methods to determine of an unknown structure proceeds in 3 major steps generally. So, first, the shape and size of the unit cells are deduced from the angular positions of the diffraction lines. Second, the number of atoms per unit cell is then computed from the shape and size of the unit cell, the chemical compositions of the specimens and its measured density. And the third is finally, the positions of the atoms within the unit cells are deduced from the relative intensities of the diffraction lines. So, first what we are doing about the preliminary treatment of the data. So, the specimen preparations must ensure the random orientations of the individual particles of powder if the observed relative intensities of the diffraction lines are to have any meaning in terms of crystal structure. After the pattern is obtained, the value of sin square theta is calculated for each diffraction line. This set of sin square theta value is the raw material for the determination of cell size and shape, or one can calculate the d value, which is the inter layer distance of each line from this set of numbers. Ensure that the observed pattern does not contain any extraneous lines. The ideal pattern contains lines formed by X-rays of a single wavelength diffracted only by the substance whose structure is to be determined, because the whatever the peaks actually we are getting, now we are going to determine or maybe we are going to do the treatment only for those peaks. If there is some extra peaks comes, so that can be possible maybe by 2 sources. So, first one is known as the diffraction of X-rays having wavelength different from that of the principal component of the radiations, and diffractions by substances other than the unknown. So, now we are going to discuss about the testing the possibility of the extraneous lines, why it may occur. So, most intense lines of the pattern is the k alpha. Using k alpha and 2 theta alpha, calculate the d1 via Bragg's law, which is nothing but the lambda k alpha is equal to 2 d1 sin theta alpha. If k beta radiation is present, that is why in our previous lectures we have already discussed that we are going to use some kind of filters to restrict the other kind of radiations over there. So, if k beta radiations is present, a diffraction peak from d1 results at a 2 theta beta different from 2 theta alpha, gives like lambda k beta is equal to 2 d1 sin theta b, theta. Relationships between diffraction angles and wavelength is lambda square k alpha by lambda square k beta into sin square theta beta is equal to sin square theta alpha. So, generally lambda square k alpha by lambda square k beta is around 1.2 for most of the radiations. If it is suspected that a particular line is due to k beta radiations, multiplication of its sin square theta beta value by lambda square k alpha by lambda square k beta will give a value equal or maybe the nearly equal or to the value of sin square theta alpha for some k alpha line on the pattern, unless the product exceeds the unity. Equations as above can be set up to test the possibility of any extraneous lines like L characteristics radiations from tungsten contaminations on the target of the X-ray tube, particularly if the tube is old. So, that time maybe some kind of extraneous lines can be generated due to that the worn out tube of the tungsten. So, now we are going to discuss about the relations between Bravais lattice and its diffraction pattern. So, generally if the Bravais lattice is simple, then reflection possibly present in all. Reflections necessarily absent is almost, it is the vice versa, that means none. For the base centered, generally H and K will be the unmixed one, but these relations apply to a cell centered on a C face, and for the absentia H and K will be the mixed one. For the body centered, H, K and L, the summation of H, K and L will be the even one, and for the absentia H plus K plus L will be the odd one. For the face centered, H, K and L will be unmixed, but for the absentia we will get the H, K and L all are in mixed conditions. So, if we see that actually what will is the allowable reflections for any crystal. So, generally for the single crystals it is all. For BCC the summations of H plus K plus L is even. For FCC H, K and L is unmixed, that means HKL all may be either even or maybe all are odd. And for the diamond crystals H, K and L are all odd or maybe all are even, or maybe H plus K plus L, which is the summations of H plus K plus L will be divisible by the 4. Now, we are going to discuss about the quadratic forms of Miller indices for the cubic crystals. So, each of the 4 common cubic lattice types has a characteristic sequence of diffraction lines described by their sequentials values. Like for simple cubic it is 1, 2, 3, 4, 5, 6, 8, 9 and so on. For the BCC it should be 2, 4, 6, 8, 10. For FCC generally it is 3, 4, 8, 11, 12 and 16, and for the diamond cubic it should be 3, 8, 11, 16. So, in this particular case what we are going to do, if a set of integers cannot be found, then the substance involved does not belong to the cubic system, and other possibilities may be some other formations like tetragonal and hexagonal that can be obtained or maybe must be explored. So, here right hand side you can see the h square plus k square plus l square is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, for simple it should be 1, 0, 0, there should not be any FCC, BCC or maybe the diamond structure. For 2 it is 1, 1, 0 or maybe BCC also it may be present like 1, 1, 0. Say suppose when you are talking about the 7, because 7 is not present, because anyhow the a square, k square plus l square value, the summation of a square plus k square plus a square is equal not is equal to 7. So, that is why for 7 it is totally silent, and if it is 9 it may be 3, 0, 0 or maybe 2, 1, 1 or maybe 2, 2, 1. Indexing patterns of the cubic crystals. So, for cubic crystals generally the indexing patterns is like this: 1 by d square is equal to h square plus k square plus l square by a square. From Back's law we know that lambda is equal to 2d sin theta. So, combining this one and this second equations, we can get sin square theta is equal to lambda square by 4a square plus h square plus k square plus l square. So, where s generally we are denoting a square plus k square plus l square as a small s is always it is an integral, and then lambda square by 4a square is constant for any one pattern, lambda is the wavelength of incident radiations and a is the lattice parameter. So, now we are going to discuss that how we are going to calculate all these things. So, steps for indexing the pattern of a cubic substance: finding a set of integers which will yield a constant quotient when divided one by one into the observed sin square theta values. Once the proper integers s are found, the indices h, k, l of each line can be written down by inspection or from the tabulations given in the next slide. So, now we are going to discuss about the indexing patterns of cubic crystals by the analytical methods. So, before going to start, first we have to establishing the conditions for a cubic crystal structure. So, for cubic crystals generally we are having sin square theta is equal to capital K into a square plus k square plus l square, where the k is the constant, that means it is equal to lambda square by 4a square. So, now that means the sin square theta 1 by h 1 square plus k 1 square plus l 1 square is equal to the theta 2 for h 2, k 2, l 2 and so on, because which all the are the constant value. So, where 1, 2, 3 etcetera refer to the lines of the pattern. So, the value of h square plus k square plus l square for any line is integer, since h, k, l are individually integers. So, in this case we have actually mentioned all the steps for these analytical methods, which I am going to discuss by slide. So, in this case simple, we have taken copper K alpha radiations value, and from that just we are going to give an example. So, here in this particular case we are having line 1 1, we are having some theta value. So, we are having theta value means these all are the obtained peaks from the XRD data. So, from that particular peaks we are getting the theta value, then we are making it sin theta and the sin square theta value. Then after that what we are doing? We are doing the sin square theta by the integers, like divided by integers like 1, 2, 3, 4, 5, 6, 8, 10, 9, 10 like that, and then we are trying to get the common value that which is matching with the line 1 1 or maybe line with line 2 2 or maybe line 2 2 with line 3 3. So, in this particular case you can see that for line 1 1 the sin square theta divided by 3 is value is 0.0469, which is more or less similar to the line 2 2 when we are dividing the sin square theta value by 4, and same thing is happening for the line 3 3 when we are dividing it by the sin square theta by 8. So, like this way we are going up to line 8 8, and then when we are getting the line 8 8, so all the commons value, say suppose for these examples we are getting the 11 means what? A square plus k square plus l square will be the 11. So, that means we are taking it as a 113, because 1 square plus 3 square, the whole summation is 11. And then in the next step also, if you see this one for the line 6 6, we are making it as 400 because it has been divided by the 16. So, a square plus k square plus l square is 16. So, 4 square plus 0 square plus 0 square, the whole summation is 16. So, how now we have to see that the characteristic sequence of the diffraction is matching with which crystal structure. So, in this case we are getting 3, 4, 8, 11, 12, 16, 19, 20, that means it is matching with the FCC crystal structure. So, we can roughly tell that the material is FCC in nature. Now, in the next slides we are going to discuss about the determinations of the lattice parameters. So, in this particular case from the last slide we have already received the value of a square plus k square plus l square. Now, we have already obtained from that value that HKL value of that one. Now, we are going to get the k value. So, k value means which is lambda square by 4a square, lambda value already we know and we know the value of k. So, we are getting the value of the a. So, here a is the lattice parameters which we are getting as 3.612 angstrom. Next we are going to discuss about the indexing patterns of cubic crystals by the mathematical methods. So, till now we are discussing about the analytical methods, now we are going to prove the same thing by the mathematics. So, for cubic crystals we are having that equation sin square theta is equal to lambda square by 4a square into a square plus k square plus l square. So, if we think it as a constant means capital K, that means sin square theta is directly proportional to the a square plus k square plus l square. So, in this particular case what we are doing? We are following the same thing, we are getting the theta value, then we are making it as a sin theta and we are making it as a sin square theta also. So, in this particular slide we have reached up to this point. Then after that what we are going to do? We are going to do the sin square theta value by divided by the sin square theta minimum value and multiply by the appropriate integers like 1, 2, 3, 4 like that, and then select the results that yields the h square plus k square plus l square, which I am going to discuss into the next slide. So, in this particular case what happened? We are getting the sin square theta value, then we are dividing this sin square theta value with the minimum sin square theta value, and then we are getting these parameters, then that is multiplied into different integers like 1, 2 and 3, and then from that we are getting the a square plus k square plus h l square value. So, from this we are getting the HKL value, and if we get the HKL value and if we put the HKL value over here, so from these particular equations we can get the value of A or maybe the lattice parameters. So, the characteristic sequence of diffraction lines here also obtain the same thing 3, 4, 8, 11, 12, 16, 19, 20 like that, and here also the Bravais lattice we are finding for this FCC is A is equal to 3.612 angstrom. So, now we are going to discuss, till now we are discussing about the cubic crystals, now we are going to discuss about the non-cubic crystals by these two methods, one is analyticals, another one is the mathematical model. So, generally for the hexagonal systems the plane spacing equations is sin square theta is equal to lambda square into 4a square multiplied by 4 by 3 h square plus hk plus k square plus l square by c by a whole square. So, in this case a and c by a are constants for given diffraction patterns. We can, if we rearrange these equations, we can get the sin square theta A. So, capital A here is nothing but the lambda square by the 3a square, and here we are confirming this c which is nothing but the lambda square by the 4c square, which are the constant. So, since h, k and l are always integers, the term is parenthesis like h square plus hk plus k square can only have values like 0, 1, 3, 4, 7, 9, 12 and l square can only have values like 0, 1, 4, 9 etc. So, now here are the steps for the analytical methods. So, here also the same thing like the cubic crystals, we have written all the steps and we will follow all these steps for next time calculations. So, first initially you have to calculate the sin square theta for the each peak. So, in this case we have already calculated the sin square theta value and then divided each sin square theta value by integers like 3, 4, 7 because that is the normal crystal structure for the hexagonal or maybe the tetragonal one. So, from h square plus hk plus k square allowed by the structure factor. Then look for the lowest common quotient. So, from this we are going to get the lowest common quotients and then the lowest common quotient is A, which is nothing but the 0.0908. So, in this particular case we are getting the common lowest value is this one, and then peaks with the lowest common quotients are HK0 type peaks. Assign allowed HK0 indices to the peaks itself. So, now after that what we are going to do? We are going to do indices correspondence to a square plus hk plus k square is equal to 1, 3, 4, 7 or maybe hk is equal to 10, 11, 20 or maybe the 21. So, that means hk is equal to 10, 11, 20 and 21. Then what we are going to do? We are going to subtract from each sin square theta value from 3a, 4a, 7a. from h square plus hk plus k square allowed by the structure factor. Look for lowest common quotient. From this you can identify 0 0 1 type peaks. The first allowed peak for the hexagonal system is 0 0 2. Determine C from the equations. If we follow the equations like CL square is equal to sin square theta minus A into h square plus hk plus k square. Since h 0 and k 0, then C is equal to LCQ by L square, which is nothing but sin square theta by L square. So, from this particular case we are getting that hk, suppose if I give the example. So, in this particular case we are getting the hkl value is 0 0 2, and if we put the L value over here, then easily we can calculate the C, and if we get the C, then we can get the L square value, which is nothing but a 4 in this particular case. So, in these particular slides, so peaks are that are not hk0 or 0 0 L can be identified the using combinations of A and C values. This is accomplished by the considering sin square theta is equal to CL square plus A into H square plus HK plus K square. So, in this particular slide you can get that sin square theta value we have obtained this one, and this is the sin square theta value calculated, and that is more or less matching with the sin square theta value obtained. By using these equations and from this particular table we can easily calculate the value of A, C and C by A ratio. And then we are going to discuss about the indexing patterns of the non-cubic crystals by the mathematical method. So, for the hexagonal systems we know sin square theta is equal to lambda square by 4 a square into 4 by 3 h square plus hk plus k square plus L square by C by A whole square. So, also we know the for hexagonal systems 1 by d square is equal to 4 by 3 into h square plus hk plus k square by a square plus L square by C square. So, in this particular case there are two terms. So, we are denoting it as A and C by A. So, in this particular case, so the pattern now be indexed in by considering the terms in brackets like 4 by 3 a square plus hk plus k square, and another term is L square plus C by A whole square. So, this is number 1 and this is number 2. So, first what we have to do in the next slides, say suppose I am giving an examples of the titanium powder. In that titanium powder we are getting the peaks over there, and then from that we are getting the 2 theta value, and we are getting the value of I by I0. Then we are making sin square theta value, or maybe we are getting the sin square theta value from this particular case. Now we are having two parameters, already I have mentioned number 1 and number 2. So, first we are going to calculate the 4 by 3 into h square plus hk plus k square value. In this particular case the L is absolutely 0, and then we are putting h value once 0, k value 0, h value 0, k value 1, h value 0, k value 2, h value 0, k value 3. Like this way we are getting this particular table, and then in the second order conditions we are determining the value of L square by C by A whole square. In this case we are assuming that h and hk value are all are the 0, and then from this particular case we are getting the value of L, we are getting the value of L square and L square by C by A whole square value. And then after that we are adding the part 1, means number 1 equations with the number 2 equations, and then with the correspondence HKL value we are adding those two parameters, and then after that just we are arranging this value from the increasing order, and then from this particular value, because it is the hexagonal in shape, so that is why 0 0 1 is not possible. So, that is why we are starting the value from calculating from 0 0 2. And then we are calculating all the values, and then the top of the total 12 values, because as per the hexagonal peaks that A1, 3, 4, 6, 7 like that, we are taking only those number of values, and then we are putting in this from where we are calculating the D and HKL, and after we know we have already calculated the A, C plus H square plus K square plus L square and the L square value. Then in this particular case look for the HK0 type of reflections and calculate A for this kind of reflections. So, here HKL value we know, so from there we can calculate the A value in this particular case. As the HKL is 1 0 0, so automatically the H square plus K square plus L square is 1, and if we see that this is for the 2 0 0, that means the H square plus K square plus L square is 4, and we are getting the A value is 2.947, and from this after that look for 0 0 1 type reflections, calculate the C for these reflections. Now we are calculating the C value in these particular positions, and then from that we are putting the L square value of that particular against that particular peak. So here the pretty good correlations with ICTD value. This is a one kind of database. Actual C by A for titanium is 1.5871, and here when we are doing the average of A value, we are getting that average value of A is 2.943, and for average of C is 4.674, and the C by A ratio is 1.588, and the actual value which is already in the ICTD value is 1.5871. So, that means it is more or less or maybe the same like our actual calculated value and with the ICTD value. So, this method effective for most powder XRD data and can yield the wrong results if XRD peaks are missing from your XRD pattern. In other words, missing peaks can cause you to assign the work wrong HKL values to a peak. Now, we are going to discuss about the effect of cell distortions on the powder pattern. So, the symmetry of crystal decreases, more peaks are observed, that means cubic correspondence to the triclinic. If cubic cell is expanded or contracted uniformly, but still remains cubic, the diffraction lines merely shift their positions, but do not increase in number, since no change in cell symmetry is involved. So, similar with the cell distortions, what happened for tetragonal, stretching cubic cell by 4% along 001 axis. For orthorhombic, stretching the tetragonal cell by 8% along 010 axis. So, in this particular case we are giving the examples in the cubic cell D200 or maybe D020 or D002 are the same, and the only one line is formed called the 200 line. So, this is the actually the 200 line has been formed. In tetragonal, this line splits into two, since now 002 plane spacing differs from the other two one. So, in this particular case we are getting the different lines for each different peaks. When the cell becomes orthorhombic, all three spacings are different and three lines are formed. So, in this particular slide we are going to discuss about the structure determinations by the number of atoms in the unit cell. So, in this case first we are going to discuss about the cubic. Generally the cell volume is capital V is equal to A cube. For tetragonal it is V is equal to A square C. So, like this way we can calculate the cell volume for cubic, tetragonal, hexagonal, rhombohedral, orthorhombic, and for the triclinic also. From this particular case we can measure the weight of all atoms in the cells also. So, like this way summation over A is equal to rho V prime by 1.66042, where rho is the density which is gram per centimeter cube and V prime is the volume of the unit cell, that is angstrom cube. If the substance is an element of atomic weight A, then summation over A is equal to N1A, where N1 is the number of atoms per unit cell. For chemical compounds, summation over A is equal to N2 into capital M, where N2 is the number of molecules per unit cell and M is the molecular weight of that particular material. So, the number of atoms per cell can be calculated from N2 and compositions of the compound itself. Now, we are going to discuss about the determinations of atom positions. So, the observed relative intensities of the diffracted beams are used to find the positions of a known number of atoms in a unit cell of known shape and size. The procedure is one of trial and error method, because there is no known general method of directly calculating the atom positions from observed intensities. What are the procedures? Number one is that a set of atom positions is assumed, intensities corresponding to these positions are calculated. Then number 2, the calculated intensities are compared with the observed ones, and the third is the process is repeated until satisfactory agreement is reached. So, how to select a structure for trial? All known structures may be classified into groups according to the kind of bonding, like ionic bonding, covalent bonding, metallic, or maybe the mixture of this, which holds the atom together, and a selection among these groups is aided by a knowledge of the probable kind of atomic bondings in the unknown phase. There are some other methods to determine the atom positions also. First one is called the space group theory. It is based on mathematical crystallography relating crystal symmetry on the atomic scale to the possible atomic arrangements which possesses that symmetry. Example, given substance is known to be hexagonal having n atom in its unit cell, then space group theory lists all possible arrangements of n atoms which will have hexagonal symmetry. So, it is a one kind of mismatch kind of things. Then the second one is that Fourier series. It is a type of infinite trigonometric series by which any kind of periodic function may be expressed. In a crystal, atoms are arranged in space in a periodic fashions. This means that the density of electrons is also a periodic function of positions in the crystal, rising to a maximum point where an atom is located and dropping to a low value in the region between atoms. Crystal can be regarded as a positional variations of electron density rather than an arrangement of atoms. X-rays are scattered by electrons and not by atoms as such. So, what is the Fourier series? Since the electron density is a periodic function of positions, a crystal may be described analytically by means of the Fourier series. So, relative intensities of the diffracted beams I is equal to function f square into p multiplied by 1 plus cos square 2 theta by sin square theta cos theta. Value of the structure factor f, because here the f is known as the structure factor. So, already we have gone through in our previous slides. So, here the structure factor f for HKL reflections in terms of the atom positions UVW is f is equal to summation over I to capital N Fn e to the power 2 pi I into HUn plus KVn plus LWn. Since the relative intensity I and the multiplicity factor P and the Bragg angle theta are known for each line of the pattern, then the structure factor for each reflection follows. But structure factor measures only the relative amplitude of each reflection, whereas requires measurement of both the amplitude and phase of one reflection relative to another f and not merely the f magnitude of f. So, now Fourier series can be used to map out the actual electron density throughout the cell and thus disclose the atom positions. So, now we are going to give an example of structure determinations, number of atoms and their positions. So, example like a intermediate phase which occurs in the cadmium tellurium systems CDTE. The specimen was reduced to powder and a diffraction pattern obtained with a Hall-Debye scalar camera and copper K alpha radiations. This pattern can be indexed on the basis of a cubic unit cell and the indices of the observed lines are given in the table. So, from this particular case we have received the 2 theta value, from there we can have calculated the sin square theta, then intensity and the HKL value. Then determination of the number of atoms in the unit cell, density of the specimen is 5.82 gram per centimeter cube, weight of all atoms in the cell summation over A is equal to rho V prime by 1.66042, which is nothing but the 5.82 into 6.46 cube by 1.66042, which is nothing but the 945. So, molecular weight of cadmium tellurium is 240.02. Number of molecules per unit cell means 945 by 240.02, which is nothing but is equal to 3.94, more or less is equal to 4. So, 4 molecules of CDT, that means 4 atoms of cadmium and 4 atoms of tellurium is present. And what is the chemical analysis? So, generally 46.6 is weight percent of cadmium and 53.8% of tellurium, equivalent to 49.8 atomic percent of CD, and can be represented by the formula like cadmium tellurium. So, if we are having one known structure, for selecting a known structure for comparison, examination of the indices listed in data table reveals that the indices of the observed lines are all unmixed, all odd or maybe all even, and that the Bravais lattice must be face centered. Covalent and ionic both kinds of bonding have been observed in the telluride structures. There are two common FCC structures of the AB type, that means containing two different atoms in equal proportions and both contain 4 molecules per unit cells. Sodium chloride ionic structure, zinc blend from zinc sulphide which is covalent in nature. Calculate the relative diffracted intensities for sodium chloride and zinc sulphide and compare them with the experiment. So, now we are going to do the comparison of sample with the sodium chloride and zinc sulphide. So, if the cadmium tellurium has the NaCl structure, the 1,1 reflection should be very weak and the 2,0,0 reflection very strong, but actually in the experiment 1,11 is strong and the 2,0,0 is not observed. So, it is almost the opposite. Sodium chloride structure is incorrect as there is no agreement between sodium chloride values and the observed intensities. The agreement between zinc sulphide values and the observed intensities is excellent except for a few minor inconsistencies among the low angle reflections, and these are due to neglect of the absorption factor. Zinc sulphide structure satisfactorily accounts for all the missing reflections like 2,0,0, 420 etc. since the calculated intensities of these reflections are all extremely low. So, in this case we are getting the 2,0,0 value here, HKL value 2,0,0, then sodium chloride structure the calculated intensities are coming 10, and for zinc sulphide also the calculated intensities are coming 10. So, that is matching with the sodium chloride and the zinc sulphide. So, result, the sample of CDTE has the structure of the zinc blend form of zinc sulphide because it is matching with this zinc sulphide. So, from this particular lecture we have got some basic principles of structure determinations and their application to deduce the crystal structure of cubic and non-cubic systems from diffraction patterns, which we have discussed in this particular lecture. Thank you.